Welcome back to the quiet between the stars. I hope you have found a comfortable place to rest because tonight we are traveling very far from home. Here is something remarkable to consider. The Milky Way contains somewhere between 200 and 400 billion stars. That number is so large that if you counted one star every second, it would take you over 6,000 years to finish. And yet, our galaxy is just one of an estimated 2 trillion galaxies scattered across the observable universe. Each one is an island of matter, drifting through an ocean of nearly perfect emptiness. Tonight, we begin our journey here, in the spiral arms of our own galaxy, where our Sun orbits the galactic center at roughly 800,000 kilometers per hour. From there, we will travel outward, past the neighboring galaxies of the local group, through the vast cosmic web of filaments and clusters, and finally into the great voids, regions of space so empty that a single galaxy might be the only structure for hundreds of millions of light years in any direction. If these quiet explorations help you find rest at the end of a long day, I would be grateful if you considered liking this video and subscribing to the channel. It helps others find their way here too. Now let your breathing slow. Let the weight of the day settle. We are about to leave Earth behind, and the universe is waiting. In the beginning, there was no light. The universe, roughly 380,000 years after its explosive birth, had cooled enough for electrons to bind with protons, forming neutral hydrogen atoms. This moment, called recombination, released the cosmic microwave background radiation that still permeates all of space today at a temperature of just 2.7 Kelvin. But with light now free to travel unimpeded, the cosmos entered what astronomers call the Dark Ages, a period lasting several 100 million years when no stars yet burned, no galaxies yet existed, and the universe drifted in near-perfect darkness. Yet within this darkness, something was already at work. Dark matter, that mysterious substance comprising roughly 27% of the universe's total energy density, had begun its patient labor. Unlike ordinary matter, dark matter does not interact with light. It neither emits nor absorbs photons. It reveals itself only through gravity, and gravity even in those early epochs was enough. The universe was not perfectly smooth. Quantum fluctuations from the first fraction of a second after the Big Bang had imprinted tiny variations in density. Differences of perhaps 1 part in 100,000. These variations, stretched to cosmic scales by inflation, became the seeds of all structure. Where dark matter was slightly denser, its gravitational pull was slightly stronger. Over millions of years, these regions drew in more dark matter from their surroundings, growing incrementally denser while neighboring regions grew emptier. This process, called gravitational collapse, proceeded according to well-understood physics. A region with excess mass attracts surrounding material. As that material falls inward, the region becomes denser still, attracting yet more matter. The mathematics of this runaway growth were first described by James Jeans in 1902, and the critical threshold for collapse, the Jeans mass, depends on the temperature and density of the medium. In the early universe, dark matter halos with masses of roughly 1 million solar masses could begin collapsing when the universe was only a few 100 million years old. These first dark matter halos were not galaxies. They contained no stars, no gas that had cooled enough to form stars. They were invisible scaffolding, gravitational wells waiting to be filled. Computer simulations of this era, run on supercomputers using billions of particles to trace the motion of a matter, reveal a cosmic web beginning to take shape. Dark matter gathered along filaments stretching millions of light years, with denser knots forming at the intersections. These knots would become the sites of the first galaxies. Ordinary matter, the baryons that make up atoms and molecules and eventually stars and planets, followed the dark matter's lead. Hydrogen and helium gas, the only elements produced in significant quantities during the Big Bang, in a ratio of roughly 75% hydrogen to 25% helium by mass, fell into the gravitational wells carved by dark matter. But unlike dark matter, baryonic matter can radiate energy. As gas fell inward and compressed, it heated up. For the gas to continue collapsing and eventually form stars, it needed to shed this heat somehow. In the primordial universe, cooling was difficult. The primary coolant available was molecular hydrogen, H2, which forms when two hydrogen atoms bond together. Molecular hydrogen can emit infrared radiation when it collides with other particles, carrying away thermal energy. But molecular hydrogen is fragile. Ultraviolet light easily breaks it apart, and even the cosmic microwave background, still relatively warm in those early times, could dissociate it. The cooling rate was slow, perhaps allowing gas to lose only a few degrees per million years in the smallest halos. This inefficient cooling meant that only the most massive dark matter halos could host gas dense and cool enough to form stars. Simulations suggest that halos with masses between 100,000 and 1 million solar masses, called mini-halos, were the first sites where baryonic matter could accumulate in sufficient quantities. Within these mini-halos, gas settled toward the center, gradually reaching densities of perhaps 10,000 particles per cubic centimeter, still far less dense than Earth's atmosphere, but enough to begin the next stage of collapse. The gas that collected in these early halos had a temperature of roughly 200 to 1000 Kelvin, much warmer than the molecular clouds that form stars in the present-day Milky Way, which hover around 10 to 20 Kelvin. This higher temperature meant higher pressure, which resisted gravitational collapse. The Jeans mass in these primordial clouds was consequently much larger, perhaps 100 to 1,000 solar masses, compared to roughly 1 solar mass in modern star-forming regions. The first stars to form would therefore be massive, far more massive than typical stars today. As gas continued to accumulate and cool within the largest dark matter halos, the stage was set for the first light. But the halos themselves remained invisible, detectable only by their gravitational influence on surrounding matter. If an observer could have watched the universe at an age of 200 million years, they would have seen nothing but darkness punctuated by the fading glow of the cosmic microwave background. The structure was there, the architecture was in place, but the lights had not yet been turned on. The growth of dark matter halos followed a hierarchical pattern. Smaller halos formed first, then merged with one another to build larger structures. This bottom-up assembly, sometimes called hierarchical clustering, is a fundamental prediction of the cold, dark matter model of cosmology. A halo of 1 million solar masses might form from the merger of 10 halos, each containing 100,000 solar masses. These mergers were not violent collisions in the usual sense. Dark matter particles passed through one another like two clouds of fog interpenetrating. The halos simply combined their gravitational influence, their particles settling into new orbits around a common center of mass. By the time the universe reached an age of roughly 400 million years, the largest dark matter halos had grown to masses of 100 million solar masses or more. These halos, sometimes called atomic cooling halos, were massive enough that infalling gas could be heated to temperatures above 10,000 Kelvin. At these temperatures, hydrogen atoms become ionized, and the gas can cool efficiently through atomic line emission, particularly the Lyman alpha transition of hydrogen at a wavelength of 121.6 nanometers. This more efficient cooling allowed gas to collapse more rapidly, reaching higher densities and setting the stage for sustained star formation. The transition from mini-halos to atomic cooling halos marked a critical threshold in cosmic history. In mini-halos, star formation was sporadic and self-limiting. The radiation from the first massive stars could easily destroy the molecular hydrogen in surrounding gas, shutting off further cooling and preventing additional stars from forming. But in atomic cooling halos, the gas was dense enough and the gravitational well deep enough that star formation could proceed more continuously. These halos were the true progenitors of galaxies. Within these larger halos, gas did not simply fall straight to the center. Conservation of angular momentum, a fundamental principle of physics, ensured that infalling material retained whatever rotational motion it possessed. Gas clouds in the early universe were not perfectly still. They had been set spinning by tidal torques from neighboring structures, gravitational tugs that imparted a gentle rotation. As the gas collapsed, this rotation sped up, just as a figure skater spins faster when pulling in their arms. The result was the formation of a rotating disk of gas at the center of the dark matter halo. These primordial gas disks were the embryonic forms of spiral galaxies. They were small by modern standards, perhaps only a few thousand light-years across, compared to the Milky Way's disk diameter of roughly 100,000 light-years. But they contained the essential ingredients: a reservoir of hydrogen and helium gas, a gravitational well provided by the dark matter halo, and the rotational support that would allow the disk to persist rather than collapsing immediately into a single massive object. The density of gas in these early disks was not uniform. Small perturbations, inherited from the same primordial fluctuations that seeded the dark matter halos, created regions of slightly higher density. These overdense regions attracted surrounding gas, growing denser still. When the density became high enough and the temperature low enough, gravity finally overcame pressure, and the gas began to collapse into the first stars. The Dark Ages were about to end, and the universe was about to be transformed by light. The collapse began in darkness, but it would not end there. Within those primordial gas clouds, clumps of hydrogen and helium fell inward under their own weight, accelerating as they contracted. Unlike the gentle, gradual processes that would characterize later generations of star formation, this first collapse was violent and unimpeded. There were no heavy elements to radiate away energy efficiently, no dust grains to cool the gas, no magnetic fields threaded through the medium to slow the infall. The gas could only cool through the emission of molecular hydrogen radiation, a process far less efficient than the cooling mechanisms available to later cosmic generations. This inefficiency had profound consequences. Because the gas could not shed its thermal energy quickly, it remained hot and resistant to fragmentation. The gene's mass, the minimum mass required for a gas cloud to overcome its internal pressure and collapse under gravity, scales with temperature. Hotter gas requires more mass to collapse. In the primordial universe, with gas temperatures hovering around several hundred Kelvin, the gene's mass reached values of hundreds to thousands of solar masses. The first stars, born from this hot, metal-free gas, would be giants unlike anything the modern universe produces. These were the population 3 stars, a designation that reflects the astronomical convention of numbering stellar populations in reverse order of their discovery. Population I stars, identified first, are the young metal-rich stars found in the disks of spiral galaxies. Population 2 stars, recognized later, are the older metal-poor stars inhabiting galactic halos and globular clusters. Population 3 stars, theorized last but born first, represent the primordial generation that preceded all others. No confirmed population 3 star has ever been directly observed, their existence inferred from theoretical models and the chemical signatures they left behind in subsequent stellar generations. The masses of these first stars likely ranged from tens to hundreds of solar masses, with some models suggesting individual stars exceeding 500 solar masses. For comparison, the most massive stars forming in the present-day universe rarely exceed 150 solar masses, limited by the radiation pressure of their own luminosity blowing away their outer layers. Population 3 stars could grow larger because the lack of heavy elements made their outer layers more transparent to radiation, allowing them to accumulate more mass before this limit was reached. The structure of a population 3 star differed fundamentally from modern stellar objects. With no carbon, nitrogen, or oxygen to catalyze nuclear reactions through the CNO cycle, these stars relied entirely on the proton-proton chain for hydrogen fusion. This process is less temperature-sensitive than the CNO cycle, meaning the core did not need to be as hot to sustain fusion. However, the enormous mass of these stars compressed their cores to temperatures exceeding 100 million Kelvin, far hotter than the 15 million Kelvin core of our Sun. At these temperatures, the proton-proton chain operated with ferocious efficiency, and the stars blazed with luminosities millions of times greater than solar. The surface temperatures of population 3 stars reached 50,000 to 100,000 Kelvin, compared to the Sun's modest 5,800 Kelvin. This extreme heat shifted their peak emission deep into the ultraviolet, making them appear blue-white to any hypothetical observer. But more importantly, this ultraviolet radiation carried enough energy to ionize hydrogen atoms, stripping electrons from protons across vast distances. Each massive population 3 star carved out a bubble of ionized gas in the surrounding neutral medium, a sphere of influence that could extend for thousands of light years. The lifetimes of these stellar titans were measured in millions of years rather than billions. A star of 100 solar masses burns through its hydrogen fuel in approximately 3 million years, while a star of 200 solar masses might exhaust its supply in less than 2 million years. This brevity stands in stark contrast to the Sun's 10 billion-year main sequence lifetime, or the trillions of years that the smallest red dwarf stars will persist. Population 3 stars lived fast and died young, but in their brief existence, they transformed the universe. The light from the first population 3 stars began to flood the cosmos roughly 100 to 200 million years after the Big Bang, during the epoch astronomers call cosmic dawn. This was not a single moment, but a gradual process, as stars ignited in different dark matter halos across the universe at different times. The first photons capable of ionizing hydrogen streamed outward from these nascent stellar nurseries, beginning the long process of reionization that would eventually render the entire universe transparent to ultraviolet light. The ionizing radiation from population 3 stars created expanding bubbles of ionized hydrogen, regions where the neutral gas had been stripped of its electrons. These bubbles grew as more stars formed, and as existing stars continued to pour out ultraviolet photons. Initially isolated, the bubbles eventually began to overlap and merge, like soap bubbles combining in a sink. By approximately 1 billion years after the Big Bang, the process was largely complete, and the intergalactic medium had transitioned from neutral to ionized. This epoch of reionization represents one of the major phase transitions in cosmic history, fundamentally altering the optical properties of the universe. But population 3 stars contributed more than just ionizing radiation. Their deaths, when they came, were spectacular and consequential. Stars with masses between roughly 140 and 260 solar masses met their end through a mechanism called pair instability supernovae. In the cores of these massive stars, temperatures exceeded 1 billion Kelvin, hot enough for gamma-ray photons to spontaneously convert into electron-positron pairs. This pair production removed pressure support from the core, triggering a runaway collapse. The subsequent thermonuclear detonation was so violent that it completely destroyed the star, leaving no remnant behind and dispersing all the heavy elements synthesized during the star's life and death into the surrounding gas. A pair instability supernova released energy equivalent to 10 to 100 times that of a typical core collapse supernova, with peak luminosities rivaling entire galaxies. The explosion ejected tens of solar masses of newly forged elements: oxygen, silicon, magnesium, and iron, created in the final moments of nuclear burning and the explosive nucleosynthesis of the detonation itself. These elements, scattered into the primordial gas, would be incorporated into the next generation of stars, beginning the process of chemical enrichment that continues to this day. Stars at the lower end of the population 3 mass range, between roughly 25 and 140 solar masses, died as core collapse supernovae, similar in mechanism to the deaths of massive stars today. Their cores collapsed into neutron stars or black holes, while their outer layers were expelled in powerful explosions. These events also contributed heavy elements to the surrounding medium, though in different proportions than pair instability supernovae. The chemical fingerprints of these different explosion types can still be detected in the oldest surviving stars, ancient objects that formed from gas enriched by the first stellar generation. The most massive population 3 stars, those exceeding approximately 260 solar masses, faced a different fate. At these extreme masses, the pair instability mechanism triggered a collapse so rapid that the star fell directly into a black hole before a supernova explosion could develop. These direct collapse black holes retained most of the star's mass, potentially forming seed black holes of several hundred solar masses. Some theorists propose that these seeds, through subsequent accretion and mergers, grew into the supermassive black holes that now inhabit the centers of galaxies, though this remains an active area of research. The transition from population 3 to population 2, star formation occurred when the heavy element abundance in the gas reached a critical threshold. Even trace amounts of carbon and oxygen, at levels 1/10,000th of solar abundance, dramatically enhanced the cooling efficiency of collapsing gas clouds. These elements could radiate energy through fine structure emission lines, allowing the gas to cool to much lower temperatures than pure hydrogen and helium. Cooler gas meant lower Jeans masses, which meant smaller stars could form. The era of stellar giants gave way to a more diverse population, including the first low-mass stars capable of surviving to the present day. Some of these ancient survivors still exist, orbiting in the halos of galaxies like the Milky Way. Stars like SMSSJ 03130036-670839.3, discovered in 2014, contain iron abundances less than 1/10,000,000th of solar, making them among the most metal-poor stars ever observed. Their chemical compositions bear the signatures of enrichment by a single or small number of population 3 supernovae, providing direct evidence of the nucleosynthetic processes that operated in the first stellar generation. These stellar fossils serve as time capsules, preserving information about conditions in the early universe that would otherwise be lost. The first light in the universe was not gentle. It was the fierce ultraviolet glare of massive, short-lived stars, burning through their fuel at prodigious rates, ionizing the gas around them, and dying in explosions that seeded the cosmos with the elements necessary for planets and life. This light ended the Dark Ages and began the long process of cosmic chemical evolution. The universe, once a sea of neutral hydrogen, was being transformed into something far more complex, one stellar generation at a time. Those first stellar generations, burning bright and dying young, left behind more than heavy elements. They left behind motion. The gas clouds from which they formed had never been perfectly still, even in the earliest moments, as dark matter halos pulled baryonic matter inward. Slight asymmetries existed. A cloud might have been nudged by a neighboring density fluctuation, or tugged unevenly by the gravitational influence of a passing clump of dark matter. These tiny imbalances, almost imperceptible in the vast primordial soup, carried consequences that would shape every galaxy in the observable universe. Angular momentum, once acquired, cannot simply disappear. This is one of the most fundamental conservation laws in physics, as inviolable as the conservation of energy itself. When a cloud of gas begins to collapse under gravity, any initial rotation it possesses must be preserved. But as the cloud shrinks, something remarkable happens. Just as a figure skater spins faster when she pulls her arms inward, a contracting gas cloud must spin faster as its radius decreases. The mathematics are precise. Angular momentum equals mass times velocity times radius. If mass stays constant and radius shrinks, velocity must increase proportionally. Consider a primordial gas cloud spanning perhaps 100 kiloparsecs, roughly 326,000 light-years across. Such a cloud might have an initial rotation velocity of only a few kilometers per second, barely perceptible against the cosmic background. But as this cloud collapses to form a galaxy 1/10 its original size, that rotation velocity increases tenfold. Collapse further to a disk spanning 30 kiloparsecs like our own Milky Way, and the rotation speeds climb to hundreds of kilometers per second. The Sun, located about 26,000 light-years from the galactic center, orbits at approximately 230 kilometers per second, completing one circuit around the galaxy every 225 to 250 million years, a period sometimes called a galactic year. This process of collapse and spin-up explains why so many galaxies are flat. A spherical cloud of gas with any rotation at all cannot collapse equally in all directions. Along the axis of rotation, gravity pulls material inward without opposition. But perpendicular to this axis, in the plane of rotation, centrifugal effects resist the inward pull. The cloud flattens, like pizza dough spun by a chef, settling into a disk configuration where gravitational attraction towards the center is balanced by the centrifugal tendency of orbiting material to fly outward. This equilibrium, called rotational support, is what gives spiral galaxies their characteristic thin disk structure. The Milky Way's disk is remarkably thin relative to its width. While the galaxy spans roughly 100,000 light-years in diameter, its stellar disk has a scale height of only about 1,000 light-years for older stars, and merely 300 light-years for the youngest stellar populations, and gas. This ratio, roughly 100:1, reflects the efficiency with which angular momentum flattens rotating systems. The gas from which new stars form is even more confined, tracing a thin layer along the galactic mid-plane where density is highest and gravitational potential is deepest. Not all the material in a collapsing protogalaxy ends up in the disk, however. Some gas, particularly that which fell in early before the disk had fully formed, or which arrived along trajectories misaligned with the eventual rotation axis, ended up in a spheroidal distribution surrounding the disk. This component, called the stellar halo, contains some of the oldest stars in the galaxy, many of them 12 to 13 billion years old. These ancient stars orbit on elongated, randomly oriented paths, their motions preserving the chaotic conditions of the galaxy's earliest assembly. Globular clusters, dense spherical collections of hundreds of thousands of stars, also inhabit this halo region, orbiting the galactic center on trajectories that take them far above and below the disk plane. The bulge at the center of many disk galaxies represents another population with distinct kinematics. Classical bulges found in galaxies like the Sombrero Galaxy, Messier 104, are pressure-supported systems where stars move on randomly oriented orbits much like the stellar halo but concentrated in the galactic center. These structures may have formed from early mergers or rapid collapse before the disk fully assembled. Pseudobulges, in contrast, show significant rotation and may have formed gradually from disk material funneled inward by gravitational instabilities. The Milky Way's bulge appears to be a complex structure, possibly a bar seen end-on, with a peanut-shaped or X-shaped morphology revealed by infrared surveys that can peer through the obscuring dust of the disk. The rotation of galaxies is not uniform from center to edge. If galaxies behaved like solid wheels, outer regions would move faster than inner regions, maintaining the same angular velocity throughout. If they behaved like the solar system, where Kepler's laws govern planetary motion, outer regions would move slower, with orbital velocity declining as the square root of distance from the center. Neither description fits observed galaxies. Instead, most spiral galaxies exhibit flat rotation curves, where orbital velocity rises steeply in the inner regions and then remains roughly constant out to the visible edge of the disk and beyond. The Milky Way's rotation curve illustrates this pattern. Within the inner few kiloparsecs, orbital velocities rise rapidly, reaching about 200 kilometers per second by 5 kiloparsecs from the center. Beyond this point, the curve flattens, hovering between 200 and 240 kilometers per second out to at least 60 kiloparsecs, well beyond the visible stellar disk. The Andromeda Galaxy, Messier 31, shows similar behavior, with rotation velocities of approximately 250 kilometers per second maintained across its disk. These flat rotation curves, first measured systematically by Vera Rubin and Kent Ford in the 1970s, provided some of the most compelling evidence that galaxies are embedded in vast halos of invisible matter. The physics behind rotation curves connects directly to the distribution of mass within galaxies. For a star orbiting at radius r with velocity v, the gravitational acceleration toward the center must exactly balance the centripetal acceleration required for circular motion. This balance yields a simple relationship. The mass enclosed within radius r equals v squared times r divided by the gravitational constant g. If velocity remains constant as radius increases, then enclosed mass must increase linearly with radius. But the visible stars and gas in galaxies do not follow this distribution. Their density drops off exponentially beyond a certain scale length, typically 3 to 4 kiloparsecs for the Milky Way's disk. Something else must be providing the gravitational pull that keeps outer stars moving so fast. That something is dark matter, distributed in an extended halo that dwarfs the visible galaxy. While the Milky Way's stellar disk contains perhaps 60 billion solar masses, and its gas contributes another 10 billion, the dark matter halo is estimated to contain roughly 1 trillion solar masses, extending to a virial radius of perhaps 200 kiloparsecs. This invisible scaffold, detectable only through its gravitational influence, determines the overall rotation properties of the galaxy. The visible disk, with all its stars and gas and dust, is merely a luminous tracer embedded within a far larger dark structure. The specific angular momentum of galaxies, the angular momentum per unit mass, follows patterns that reveal their formation history. Disk galaxies have high specific angular momentum, their material having retained much of the spin acquired during initial collapse. Elliptical galaxies, by contrast, have low specific angular momentum, their stars moving on randomly oriented orbits that largely cancel out any net rotation. This difference reflects different formation pathways. Disk galaxies formed through relatively quiescent collapse and accretion, preserving angular momentum. Ellipticals formed through violent mergers that scrambled stellar orbits and converted ordered rotation into random motion. Within disk galaxies, angular momentum is not distributed uniformly. The inner regions, where material fell in first and had less time to acquire spin from tidal torques, have lower specific angular momentum than outer regions. This gradient helps explain why galactic disks have exponential surface brightness profiles, with stellar density declining smoothly from center to edge. Material with low angular momentum settles close to the center, while high angular momentum material spreads to larger radii. The scale length of this exponential profile, typically 2 to 5 kiloparsecs for Milky Way-sized galaxies, reflects the overall angular momentum content of the protogalactic cloud. Bars, those elongated stellar structures found in roughly 2/3 of disk galaxies, represent a redistribution of angular momentum within galactic disks. When a disk becomes gravitationally unstable, it can develop a bar-shaped perturbation that rotates as a rigid pattern through the stellar population. Stars within the bar follow elongated orbits aligned with the bar's major axis, while stars outside the bar are influenced by its gravitational potential as it sweeps past. This interaction transfers angular momentum outward, from the inner disk to the outer disk and halo. The bar itself may slow its rotation over time, a process called dynamical friction, as it loses angular momentum to the surrounding dark matter halo. The Milky Way possesses such a bar, extending roughly 10,000 light-years from the galactic center and oriented at an angle of about 25 to 30 degrees relative to the line connecting the Sun to the galactic center. This bar rotates with a pattern speed of approximately 40 kilometers per second per kiloparsec, completing one rotation in roughly 150 million years. Its presence influences the orbits of stars throughout the inner galaxy, creating resonances where stellar orbits become trapped in specific patterns relative to the bar's rotation. Angular momentum also governs the behavior of gas within galaxies. Unlike stars, which pass through each other during galactic interactions without colliding, gas clouds can collide, shock, and lose energy through radiation. This dissipation allows gas to sink toward the galactic center, but only if it can shed angular momentum in the process. Gravitational torques from bars and spiral arms provide one mechanism for this transfer, funneling gas inward where it can fuel star formation or feed the central supermassive black hole. Without such mechanisms, gas would remain trapped at large radii, unable to participate in the ongoing evolution of the galactic center. The conservation of angular momentum thus shapes galaxies at every scale, from the overall flattening of disks spanning tens of thousands of light-years to the spiraling infall of gas clouds mere parsecs from central black holes. It determines which galaxies spin rapidly and which barely rotate at all. It influences where stars form, how bars develop, and how galaxies respond to interactions with their neighbors. This single physical principle, discovered in the context of spinning tops and orbiting planets, governs the architecture of structures containing hundreds of billions of stars. The architecture shaped by angular momentum reveals itself most dramatically in the spiral arms that wind through disk galaxies. These luminous bands, traced by young blue stars and glowing nebulae, appear to sweep outward from galactic centers like the arms of a cosmic pinwheel, yet their nature defies intuition. They are not material structures in the conventional sense, not collections of stars bound together and rotating as fixed patterns. Instead, they represent something more subtle. Waves of compression moving through the galactic disk, regions where matter temporarily crowds together before dispersing again. The puzzle of spiral arms troubled astronomers for decades. If these structures were simply material features, composed of the same stars rotating together around the galactic center, they would face an insurmountable problem. Stars at different distances from the center orbit at different speeds. In the Milky Way, the Sun completes one orbit in approximately 230 million years, traveling at about 220 kilometers per second. Stars closer to the center orbit faster, completing their circuits in less time. Stars farther out move more slowly through space and take longer to complete each revolution. This differential rotation, observed in all disk galaxies, would wind up any material spiral arm within a few galactic rotations. After perhaps 500 million years, the arms would wrap around the galaxy so many times they would blur into an indistinct disk. Yet spiral galaxies billions of years old display crisp, well-defined arms. Something prevents the winding. The resolution came through density wave theory, developed primarily by Chia-Chiao Lin and Frank Xu in the 1960s. They proposed that spiral arms are not collections of specific stars, but rather waves of enhanced density propagating through the galactic disk. The analogy to traffic flow illuminates the concept. On a highway, a region of slowed traffic can persist for hours even as individual cars pass through it. Drivers enter the congested zone, slow down, then accelerate out the other side. The jam itself remains roughly stationary or moves slowly relative to the road, while the cars composing it change continuously. Spiral arms function similarly. Stars and gas clouds enter the arm, experience compression, then exit and continue their orbits. The wave pattern rotates as a coherent structure, but the material passing through it changes constantly. The mathematics describing these waves involves gravitational perturbations propagating through a rotating disk. Small deviations from perfect axial symmetry can amplify through gravitational interactions, creating self-sustaining wave patterns. The pattern speed, the angular velocity at which the spiral structure rotates, differs from the rotation speed of the disk material. In the Milky Way, the spiral pattern rotates at roughly 25 to 30 kilometers per second per kiloparsec, slower than the circular velocity of stars at most radii. This means that at the Sun's location, approximately 8 kiloparsecs from the galactic center, stars overtake the spiral pattern from behind, passing through the arms roughly every 100 million years. The consequences for star formation prove profound. As gas clouds approach a spiral arm, they encounter the density wave from behind. The gravitational potential of the arm, enhanced by the accumulated mass of stars and gas already within it, pulls on the approaching cloud. The cloud accelerates slightly, then enters a region where the gas density increases by factors of 2 to 10 compared to the interarm regions. This compression triggers gravitational instabilities within the cloud. Regions that were marginally stable against collapse now find themselves pushed over the threshold. The increased density raises the self-gravity of cloud cores, overwhelming the thermal pressure and turbulence that previously supported them. The compression occurs relatively gently by cosmic standards. Gas enters the arm at perhaps 10 to 20 kilometers per second relative to the pattern, slow enough that the compression remains subsonic in most cases. Yet even this modest squeezing suffices to initiate collapse in clouds already near the critical density. Giant molecular clouds, containing 100,000 to several million solar masses of gas, fragment into smaller cores. These cores contract over timescales of hundreds of thousands to millions of years, eventually forming new stars. The most massive stars that form in these compression events live fast and die young. A star of 20 solar masses exhausts its hydrogen fuel in roughly 10 million years, a mere instant compared to the galactic rotation period. Such stars never travel far from their birthplaces before exploding as supernovae. This explains why spiral arms appear so luminous in blue light. They contain disproportionate numbers of young, massive, hot stars that have not yet had time to drift away. The arms do not contain more stars overall than the interarm regions. They contain more of the brightest stars, the ones that dominate the visual appearance of galaxies. Observations across the electromagnetic spectrum reveal the sequential nature of star formation in spiral arms. Radio telescopes detect molecular gas, primarily traced by carbon monoxide emission, concentrated along the inner edges of spiral arms, where compression first occurs. Infrared observations reveal embedded protostars, still shrouded in the dusty cocoons from which they formed. Optical light shows the young stellar associations that have cleared away their natal material. Ultraviolet emission traces the hottest, most massive stars, typically found slightly downstream from the peak gas density. This spatial sequence, spanning perhaps 500 to 1,000 parsecs across the arm, represents a temporal sequence of star formation triggered by the passage of the density wave. The Milky Way displays this structure clearly, though our position within the disk complicates observation. We reside in a minor structure called the Orion Spur, located between the more prominent Sagittarius and Perseus arms. The Sagittarius arm lies roughly 2 kiloparsecs closer to the galactic center, while the Perseus arm extends about 2 kiloparsecs farther out. Radio surveys of hydrogen and carbon monoxide have mapped these structures across much of the galaxy, revealing a pattern with 2 major arms and several smaller spurs and branches. The exact number and configuration of arms remains debated, with estimates ranging from 2 to 4 major structures, depending on the tracer used and the analysis method applied. External galaxies offer cleaner views of spiral structure. Messier 51, the Whirlpool Galaxy, located 23 million light-years away in the constellation Canes Venatici, displays perhaps the most iconic spiral pattern known. Its 2 prominent arms wind outward from a bright central region, their structure enhanced by ongoing interaction with a smaller companion galaxy. The gravitational tug of this companion has amplified the density wave, producing arms of unusual clarity and symmetry. Observations show the expected pattern. Molecular gas concentrated along the inner arm edges, young stellar clusters distributed throughout the arms, and older red stars spread more uniformly across the disk. Not all spiral galaxies display the same arm structure. Grand design spirals like Messier 51 show two well-defined, symmetric arms extending across the entire disk. These patterns often result from gravitational interactions with companion galaxies or from strong bars in the galactic center that drive coherent waves outward. Flocculent spirals, by contrast, display numerous short, fragmented arm segments without global symmetry. NGC 2841, located 46 million light-years away, exemplifies this type. Its arms appear as patches and filaments rather than continuous sweeping curves. The star formation in such galaxies occurs in localized regions without the organized triggering seen in grand design systems. The distinction between these types relates to the strength and coherence of the underlying density wave. Strong global waves produce grand design patterns. Weaker, more localized perturbations create flocculent structure. Many galaxies fall between these extremes, displaying 2 or 3 prominent arms, along with numerous smaller spurs and branches. The Milky Way itself may belong to this intermediate category, with evidence for both large-scale arm structure and significant local irregularities. Bars add another layer of complexity to spiral structure. Roughly 2/3 of disk galaxies contain stellar bars, elongated concentrations of stars extending across their central regions. The Milky Way hosts such a bar, approximately 10,000 light-years in length, oriented at roughly 45 degrees to our line of sight toward the galactic center. Bars rotate as rigid structures, maintaining their shape as they turn. Where the ends of the bar meet the disk, they drive spiral density waves outward. The gravitational potential of the rotating bar continuously pumps energy into these waves, maintaining spiral structure over billions of years. The physics of bar-driven spirals involves resonances between the bar rotation and the orbital frequencies of disk stars. At certain radii, stars complete exactly 2 radial oscillations for every orbit around the galaxy, or 3 oscillations for every 2 orbits. These resonance locations concentrate stellar orbits, enhancing the spiral pattern at specific distances from the center. The corrotation radius, where stars orbit at the same angular speed as the bar, marks a particularly important boundary. Inside corrotation, material flows inward along the bar. Outside, it flows outward along the spiral arms. This circulation redistributes angular momentum throughout the disk, slowly evolving the galactic structure over cosmic time. The redistribution of angular momentum tells only part of the story of galactic evolution. Some galaxies followed a different path entirely, one where ordered rotation gave way to random motion, where the elegant pinwheel structure never formed at all. These are the elliptical galaxies, stellar systems supported not by the centrifugal force of spinning disks, but by the chaotic velocities of their individual stars. Consider the difference in architectural terms. A spiral galaxy resembles a spinning disk of water, its stars flowing in roughly circular orbits, like leaves caught in a gentle whirlpool. An elliptical galaxy resembles a swarm of bees, each star tracing its own elongated path through the gravitational potential, the collective motion appearing almost random when viewed from any single direction. This fundamental distinction in dynamics produces profoundly different structures, different stellar populations, and different evolutionary histories. The physics underlying pressure-supported systems begins with a concept called velocity dispersion. In an elliptical galaxy, stars do not share a common rotational velocity. Instead, they move in all directions with a range of speeds, typically between 150 and 350 kilometers per second, depending on the galaxy's mass. This random motion creates an outward pressure, analogous to the thermal pressure that prevents a gas cloud from collapsing. The stars themselves act like particles in an extremely diffuse gas, their collective kinetic energy balancing the inward pull of gravity. The virial theorem, a fundamental relationship in gravitational physics, describes this equilibrium precisely. The total kinetic energy of the stellar motions equals exactly half the magnitude of the gravitational potential energy, a balance maintained over billions of years. Messier 87, the giant elliptical galaxy at the heart of the Virgo cluster, exemplifies this pressure-supported architecture. Located approximately 53 million light-years from Earth, M87 contains roughly 1 trillion stars, perhaps 10 times the stellar population of the Milky Way. Yet despite this enormous mass, the galaxy shows almost no organized rotation. Its stars swarm through a roughly spherical volume spanning 120,000 light-years in diameter, each following an orbit determined by the combined gravitational pull of all the others, plus the massive dark matter halo enveloping the visible structure. The velocity dispersion in M87's central regions reaches 375 kilometers per second, stars moving faster than the Milky Way's orbital velocity at the Sun's position, yet traveling in essentially random directions. The shapes of elliptical galaxies reveal the underlying orbital structure of their stellar populations. Astronomers classify these systems by their apparent ellipticity, from E0 galaxies that appear perfectly circular to E7 galaxies that appear highly elongated. This classification, however, captures only the projected shape on the sky. The true three-dimensional forms prove far more complex. Some ellipticals are genuinely spherical, their stars distributed isotropically with equal velocity dispersions in all directions. Others are oblate spheroids, flattened like a beach ball someone sat upon, with slightly more motion in the equatorial plane than perpendicular to it. Still others are prolate, elongated like a rugby ball, or triaxial, with 3 different axis lengths and correspondingly complex orbital families. The orbital families within triaxial ellipticals demonstrate remarkable mathematical elegance. Box orbits carry stars on paths that fill 3-dimensional rectangular volumes over time, the star oscillating back and forth along each axis independently. Tube orbits confine stars to donut-shaped regions, circulating around one axis while oscillating along the others. Loop orbits trace figure-8 patterns through the galactic center. Each orbital family responds differently to perturbations, and the relative populations of these families determine the galaxy's overall shape and stability. A galaxy dominated by box orbits tends toward triaxiality, while one dominated by tube orbits maintains a more axisymmetric structure. The stellar populations within elliptical galaxies differ systematically from those in spirals. Ellipticals contain predominantly old stars, typically 8 to 12 billion years in age, with very little ongoing star formation. The color of an elliptical galaxy appears distinctly red when compared to the blue tinge of spiral arms, a direct consequence of stellar evolution. Young, massive blue stars burn through their hydrogen fuel rapidly, living only millions of years before exploding as supernovae or collapsing into compact remnants. Old, low-mass red stars persist for tens of billions of years, accumulating over cosmic time. An elliptical galaxy that ceased forming stars 10 billion years ago retains only these long-lived red dwarfs and red giants, giving the entire system its characteristic warm glow. The metallicity of elliptical galaxy stars, meaning their content of elements heavier than helium, follows a distinctive pattern. Central regions contain stars with higher metallicity than the outskirts, a gradient that reflects the history of chemical enrichment. When supernovae exploded in the early galaxy, they ejected heavy elements into the surrounding gas. This enriched material fell toward the center under gravity's influence, where subsequent generations of stars incorporated the metals into their compositions. The metallicity gradient in a typical giant elliptical spans roughly a factor of 3, from perhaps twice the solar metallicity at the center to 2/3 solar metallicity at the effective radius, the distance containing half the galaxy's total light. NGC 1277, a compact elliptical galaxy in the Perseus cluster, presents an extreme case of early stellar population formation. Located 220 million light-years away, this galaxy contains stars that formed almost exclusively within the first 2 billion years of cosmic history. Spectroscopic analysis reveals stellar ages uniformly exceeding 10 billion years, with essentially no stars younger than this threshold. NGC 1277 represents a relic, a galaxy that assembled rapidly in the early universe and then simply stopped. Its star formation quenched before the universe reached 1/5 its current age. The mechanism of this quenching likely involved the supermassive black hole at its center, which contains approximately 17 billion solar masses, one of the most massive black holes known relative to its host galaxy's size. The formation pathways leading to elliptical galaxies involve violent processes that destroy ordered rotation. The most significant pathway is the merger of disk galaxies, a gravitational collision that scrambles the organized orbital motion of both progenitors. When two spiral galaxies approach each other, tidal forces first distort their shapes, pulling out long streamers of stars and gas. As the galaxies interpenetrate, their dark matter halos merge relatively smoothly, but the stellar disks experience gravitational shocking. Stars that previously followed nearly circular orbits find themselves deflected onto elongated, randomly oriented trajectories. The merger remnant, after several billion years of dynamical relaxation, settles into the pressure-supported configuration characteristic of ellipticals. Computer simulations of galaxy mergers reproduce this transformation with remarkable fidelity. Two disk galaxies, each containing 100 billion solar masses of stars and dark matter, approach each other at relative velocities of 200 to 500 kilometers per second. The first passage strips material from the outer regions, creating tidal tails that can extend hundreds of thousands of light years. The galaxies swing past each other, slow under mutual gravitational attraction, and fall back together. The second passage proves more violent, the cores now closer together, the tidal disruption more severe. After 3 to 5 close passages spanning 1 to 3 billion years, the two galaxies coalesce into a single system. The resulting object shows the smooth light distribution, random stellar motions, and old stellar population characteristic of observed elliptical galaxies. The gas content of merging galaxies determines whether the remnant continues forming stars or becomes truly quiescent. Gas-rich mergers, common in the early universe when galaxies contained larger reservoirs of cold hydrogen, trigger intense starbursts during the collision. The compression of gas clouds as the galaxies interpenetrate ignites rapid star formation, consuming much of the available fuel within a few 100 million years. Gas-poor mergers, more common in the present-day universe among already evolved systems, produce ellipticals without significant new star formation. The distinction explains why some elliptical galaxies show traces of recent stellar activity, while others appear completely dormant. The scaling relations among elliptical galaxies reveal deep connections between their structural properties. The Faber-Jackson relation, discovered in 1976, connects luminosity to velocity dispersion. Brighter ellipticals have higher velocity dispersions, following a power law where luminosity scales roughly as the fourth power of velocity dispersion. A galaxy with twice the velocity dispersion appears approximately 16 times more luminous. This relationship emerges from the virial theorem, combined with the observation that elliptical galaxies have roughly similar mass-to-light ratios and surface brightnesses. The fundamental plane extends this relationship to 3 dimensions, incorporating the effective radius alongside luminosity and velocity dispersion. Elliptical galaxies do not scatter randomly through this 3-dimensional parameter space, but instead cluster tightly around a 2-dimensional surface, the fundamental plane itself. The thinness of this plane, with scatter of only about 15% in any direction, indicates that elliptical galaxies form a remarkably homogeneous family. Despite their range in mass spanning factors of 10,000, the physical origin of the fundamental plane remains an active area of research, likely involving systematic variations in dark matter content, stellar population age, and formation history across the elliptical galaxy population. The homogeneity of massive elliptical galaxies stands in stark contrast to the diverse and often chaotic structures found at smaller scales. Dwarf galaxies, those containing fewer than a few billion stars, represent the most numerous type of galaxy in the universe. Yet their physics operates under fundamentally different constraints than their larger cousins. Where massive galaxies retain their gas, regulate their star formation, and maintain coherent structures over billions of years, dwarf galaxies live precarious existences, vulnerable to internal explosions and external forces that can reshape or even destroy them entirely. The smallest galaxies blur the boundary between what constitutes a galaxy and what might be called merely a star cluster. ultra-faint dwarf galaxies, discovered in increasing numbers around the Milky Way since 2005, contain as few as 1,000 stars spread across regions hundreds of light-years in diameter. Segue 1, one of the faintest known, holds perhaps 1,000 stars within a half-light radius of only 29 parsecs, roughly 95 light-years. Its total luminosity amounts to only 340 times that of the Sun, dimmer than many individual giant stars. Yet velocity measurements of its member stars reveal something remarkable. They move with a dispersion of approximately 3.7 kilometers per second, far too fast for the visible stellar mass to gravitationally bind them. The implied mass-to-light ratio exceeds 3,000, meaning dark matter outweighs luminous matter by more than 3,000 to 1. This extreme dark matter dominance characterizes dwarf galaxies as a class. The Draco dwarf spheroidal, orbiting the Milky Way at a distance of approximately 80 kiloparsecs, contains roughly 300,000 stars within a half-light radius of 221 parsecs. Its stars move with velocity dispersions around 9 kilometers per second, implying a total mass of roughly 200 million solar masses, despite a luminosity of only 260,000 suns. The dark matter halo extends far beyond the visible stellar distribution, creating a gravitational well that holds the sparse stellar population together against tidal forces from the Milky Way. The physics governing dwarf galaxy evolution differs qualitatively from that of massive systems because of a single critical factor: the depth of the gravitational potential well. Massive galaxies like the Milky Way possess escape velocities exceeding 500 kilometers per second at their centers. Gas heated by supernova explosions, even to temperatures of millions of degrees, cannot escape such deep potential wells. The hot gas eventually radiates its energy, cools, and settles back into the disk to form new stars. This recycling sustains star formation over cosmic timescales. Dwarf galaxies face a different reality. A typical dwarf irregular galaxy with a total mass of 1 billion solar masses has a central escape velocity of perhaps 30 to 50 kilometers per second. A single supernova releases approximately 10 to the 51st ergs of energy, enough to heat surrounding gas to temperatures where thermal velocities exceed this escape threshold. Multiple supernovae, occurring in the clustered star formation typical of dwarf galaxies, can drive galactic-scale outflows that remove substantial fractions of the interstellar medium entirely. This process, called supernova-driven feedback, operates with devastating efficiency in low-mass systems. The Large Magellanic Cloud, the most massive satellite of the Milky Way, at roughly 10 billion solar masses in stars, illustrates the transition regime. Its escape velocity of approximately 90 kilometers per second at the center allows it to retain most gas heated by star formation, yet outflows still occur. The 30 Doradus region, the most luminous star-forming complex in the local group, contains the star cluster R136 with over 200 O-type stars concentrated within a radius of less than 2 parsecs. The combined stellar winds from these massive stars, blowing at speeds exceeding 2,000 kilometers per second, have carved a cavity roughly 200 parsecs across in the surrounding interstellar medium. When these stars explode as supernovae over the next few million years, they will inject additional energy that may drive gas entirely out of the large Magellanic Cloud's disk. The small Magellanic Cloud, with roughly 1/7 the stellar mass of its larger companion, shows the consequences of weaker gravitational binding more clearly. Its irregular, elongated structure stretches across roughly 4 kiloparsecs, distorted by both tidal interaction with the Large Magellanic Cloud and internal feedback processes. The Magellanic Stream, a ribbon of neutral hydrogen extending over 200 degrees across the southern sky, represents gas stripped from both Magellanic Clouds through their gravitational interaction with each other and with the Milky Way. This stream contains approximately 200 million solar masses of hydrogen, material that will never return to form stars in its parent galaxies. Irregular galaxies as a class lack the organized rotation that defines spiral structure. The Large Magellanic Cloud possesses a weak bar and hints of spiral arms, but most irregular galaxies show no coherent pattern. NGC 1569, a dwarf irregular roughly 3.4 megaparsecs distant, exemplifies the chaotic nature of star formation in these systems. Two superstar clusters, NGC 1569A and NGC 1569B, formed within the past 25 million years, each containing roughly 1 million stars packed into regions only a few parsecs across. The combined energy output from these clusters has driven a galactic superwind, visible in X-ray observations as hot gas streaming away from the galaxy at velocities exceeding 200 kilometers per second. The galaxy has lost a substantial fraction of its metals through this outflow, enriching the intergalactic medium while impoverishing its own future star formation. The metallicity of dwarf galaxies follows a clear relationship with their mass, known as the mass-metallicity relation. More massive galaxies retain more of their supernova ejecta and thus build up higher abundances of heavy elements over time. The Milky Way's interstellar medium contains oxygen at roughly 500 parts per million relative to hydrogen. The Large Magellanic Cloud, with 1/10 the Milky Way's mass, has oxygen abundances around 250 parts per million. The Small Magellanic Cloud drops to roughly 125 parts per million. The smallest dwarf spheroidal galaxies show metallicities below 50 parts per million, reflecting their inability to retain the products of stellar nucleosynthesis. This metallicity gradient has profound implications for stellar evolution within dwarf galaxies. Metal-poor gas cools less efficiently because heavy elements provide the primary cooling channels at temperatures below about 10,000 Kelvin. Carbon, oxygen, and iron atoms, when excited by collisions, radiate energy through emission lines far more effectively than hydrogen alone. Gas with lower metallicity must reach higher densities before cooling becomes efficient enough to trigger gravitational collapse. This tends to produce more massive molecular clouds and, consequently, more massive stars on average. The star formation histories of dwarf galaxies reveal remarkable diversity. Some, like the Carina dwarf spheroidal, show distinct episodes of star formation separated by billions of years of quiescence. Carina formed stars in at least 3 major bursts, one roughly 12 billion years ago, another around 7 billion years ago, and a final episode approximately 3 billion years ago. Between these bursts, star formation essentially ceased. The physical mechanism driving this episodic behavior remains debated, but likely involves the interplay between gas consumption, supernova feedback, and subsequent gas reaccretion from the surrounding halo. Other dwarf galaxies show continuous star formation extending to the present day. IC10, a dwarf irregular in the local group at a distance of 700 kiloparsecs, currently forms stars at a rate of roughly 0.05 solar masses per year, modest by Milky Way standards, but vigorous for its size. Its gas reservoir of approximately 100 million solar masses of neutral hydrogen could sustain this rate for another 2 billion years, though interactions with the Milky Way's halo may strip this gas before it can all convert to stars. The dwarf spheroidal galaxies orbiting the Milky Way present a puzzle in their near-complete absence of gas. Sculptor, Fornax, Draco, Carina, and their companions contain essentially no neutral hydrogen, despite having formed stars as recently as a few billion years ago in some cases. The leading explanation involves ram pressure stripping as these satellites pass through the diffuse hot gas halo surrounding the Milky Way. This halo, detected through X-ray observations and absorption line studies, contains gas at temperatures around 1 to 2 million Kelvin, extending to distances of at least 200 kiloparsecs. A dwarf galaxy moving through this medium at orbital velocities of 200 to 300 kilometers per second experiences pressure that can strip loosely bound interstellar gas, particularly from systems with shallow gravitational potential wells. Tidal forces from the Milky Way further sculpt the structure of its satellite population. The Sagittarius dwarf elliptical galaxy, discovered in 1994 at a distance of only 26 kiloparsecs from the galactic center, is currently being torn apart by tidal forces. Its stellar streams wrap entirely around the Milky Way, tracing its orbital path over multiple passages. The main body of Sagittarius has lost roughly half its original stellar mass to these tidal streams, and the remainder will disperse over the next billion years. This ongoing destruction demonstrates that the satellite population we observe today represents survivors of a once larger population, with many dwarf galaxies having already merged into the Milky Way's halo. The destruction of satellite galaxies feeds more than just the stellar halo. Material stripped from these smaller systems, along with gas flowing inward from the disk itself, eventually finds its way toward the gravitational center of every massive galaxy, where something far more extreme awaits. At the heart of the Milky Way, roughly 26,000 light-years from our position in the Orion Spur, lies Sagittarius A star, a supermassive black hole with a mass of approximately 4 million solar masses compressed into a region smaller than the orbit of Mercury. This object, invisible in ordinary light, reveals itself through the frantic motion of stars orbiting impossibly close to what appears to be empty space. The star S2 completes its elliptical orbit around Sagittarius, a star every 16 years, reaching speeds of nearly 7,700 kilometers per second at closest approach, just 120 astronomical units from the black hole. No ordinary concentration of matter could produce such velocities without being visible. The darkness at the center is not absence, but presence, gravity so intense that even light cannot escape. The formation of these central monsters traces back to the earliest epochs of galaxy assembly. In the dense cores of primordial gas clouds, where matter accumulated most rapidly, conditions favored the creation of massive seed black holes. The exact mechanism remains debated among astrophysicists, but several pathways appear viable. Direct collapse of pristine hydrogen gas clouds, unimpeded by the cooling effects of heavy elements, could have produced black holes of 10,000 to 100,000 solar masses within the first few 100 million years after the Big Bang. Alternatively, the rapid mergers of population 3 stellar remnants in dense nuclear star clusters might have built up similar masses through successive collisions. Whatever the initial seed, subsequent growth occurred through accretion, the steady consumption of surrounding gas and occasional stars that ventured too close. The physics of accretion determines how supermassive black holes interact with their host galaxies. Gas falling toward a black hole does not plunge directly inward. Conservation of angular momentum forces the infalling material into a flattened disk, spiraling gradually closer as friction between adjacent layers converts orbital energy into heat. These accretion disks reach temperatures of millions of degrees in their innermost regions, radiating across the electromagnetic spectrum from radio waves through X-rays. The luminosity generated can exceed the combined output of all stars in the host galaxy by factors of 100 or more. A single supermassive black hole consuming material at its maximum sustainable rate, the Eddington limit, where radiation pressure balances gravitational infall, can outshine 1 trillion suns. The relationship between black hole mass and host galaxy properties reveals a deeper connection than mere coincidence. Across galaxies spanning 4 orders of magnitude in stellar mass, the central black hole consistently contains approximately 0.1 to 0.2% of the mass of the galaxy's central bulge. This correlation, known as the M-sigma relation, links black hole mass to the velocity dispersion of stars in the surrounding bulge with remarkable precision. Galaxies with faster-moving bulge stars harbor more massive black holes, following a relationship where black hole mass scales roughly as the 4th power of stellar velocity dispersion. The tightness of this correlation implies that black holes and their host galaxies grew together, their evolution intertwined through feedback mechanisms that regulated both. M87, the giant elliptical galaxy at the center of the Virgo cluster, hosts one of the most massive black holes in the nearby universe. At 6.5 billion solar masses, this object outweighs Sagittarius, a star, by more than 1,000 times. The Event Horizon Telescope captured its shadow in 2019, revealing a dark central region, roughly 40 billion kilometers across, surrounded by a bright ring of superheated plasma orbiting at nearly the speed of light. This image, assembled from radio observations spanning the globe, confirmed decades of theoretical predictions about black hole structure. The asymmetric brightness of the ring results from relativistic beaming, with material moving toward us appearing brighter than material receding, a direct consequence of Einstein's special relativity applied to matter moving at substantial fractions of light speed. The gravitational influence of supermassive black holes extends far beyond their event horizons. Within the sphere of influence, typically spanning a few parsecs to a few hundred parsecs depending on black hole mass. Stellar orbits are dominated by the central point mass, rather than the distributed mass of surrounding stars. For Sagittarius A star, this sphere extends roughly 3 parsecs from the center, encompassing several million stars in a dense nuclear cluster. The velocity dispersion of these stars increases sharply toward the center, following Keplerian dynamics around the invisible mass. Observations of stellar proper motions in this region, tracked over decades using adaptive optics on large ground-based telescopes, provided the first definitive evidence for supermassive black holes in galactic nuclei. The feeding of supermassive black holes occurs episodically rather than continuously. Most black holes in the local universe, including Sagittarius A star, currently accrete at rates far below their theoretical maximum. Sagittarius A star consumes roughly 1 Earth mass of material per year, a trickle compared to the torrents that must have fed its growth in earlier epochs. This quiescent state reflects the depletion of easily accessible gas in the galactic center, with most available material having already been consumed or expelled by previous episodes of activity. The transition from active to quiescent represents a fundamental shift in how black holes influence their surroundings, from energetic feedback that shapes galaxy-wide star formation to passive gravitational anchors that merely organize stellar orbits. Tidal disruption events provide dramatic evidence that even quiescent black holes remain capable of spectacular feeding episodes. When a star passes within the tidal radius of a supermassive black hole, the difference in gravitational pull between the near and far sides of the star exceeds the star's self-gravity, tearing it apart. Roughly half the stellar debris remains bound to the black hole, forming a temporary accretion disk that flares to luminosities of 10 billion solar luminosities before fading over months to years. These events occur approximately once every 10,000 to 100,000 years per galaxy, providing transient glimpses of accretion physics in systems that otherwise appear dormant. The light curves and spectra of tidal disruption events encode information about both the destroyed star and the black hole that consumed it. The masses of supermassive black holes span an enormous range, from roughly 100,000 solar masses in small dwarf galaxies to tens of billions of solar masses in the most massive ellipticals. TON 618, a distant quasar, harbors a black hole estimated at 66 billion solar masses, among the largest known. At the opposite extreme, some dwarf galaxies appear to lack central black holes entirely, or host intermediate mass black holes of only a few thousand solar masses. This diversity reflects different formation histories and growth opportunities, with black holes in massive galaxies having experienced more mergers and sustained accretion episodes than their counterparts in smaller systems. The diversity of black hole masses translates directly into a diversity of luminous output when these gravitational engines actively consume surrounding material. Not all supermassive black holes shine. Most, like Sagittarius A star at the Milky Way's center, exist in a quiescent state, their accretion disks thin and faint, their energy output a mere whisper compared to their potential. But when sufficient gas falls inward, when mergers or instabilities drive fresh fuel toward the central engine, these dormant giants awaken into some of the most luminous objects in the observable universe. The physics of this awakening follows predictable patterns governed by gravity, angular momentum, and the behavior of matter under extreme conditions. Gas spiraling toward a supermassive black hole cannot fall directly inward. Conservation of angular momentum forces it into an accretion disk, a flattened structure where material orbits at tremendous speeds while gradually losing energy through friction and turbulence. The inner regions of these disks, closest to the black hole, reach temperatures of hundreds of thousands of degrees, hot enough to emit copious X-rays. Farther out, the disk glows in ultraviolet and optical wavelengths, while the outermost regions radiate in infrared. This temperature gradient, from millions of degrees near the event horizon to merely thousands at the disk's outer edge, produces a characteristic spectrum that astronomers recognize as the signature of active accretion. The luminosity of an actively accreting black hole depends primarily on two factors: the mass of the black hole itself and the rate at which material falls onto it. A black hole consuming matter at the maximum sustainable rate, the Eddington limit, produces a luminosity proportional to its mass. For a black hole of 1 billion solar masses, this Eddington luminosity reaches approximately 1.3 times 10 to the 47th ergs per second, equivalent to the combined light of several trillion sun-like stars. Such objects outshine their entire host galaxies by factors of 100 or more, their central engines visible across billions of light-years, while the surrounding stars fade into insignificance. Quasars represent the most luminous manifestation of this accretion process. First identified in the 1960s as peculiar radio sources with star-like optical appearances, quasars revealed their true nature when astronomers measured their redshifts and discovered they lay at cosmological distances. 3C273, one of the first quasars identified, shines with an apparent magnitude of 12.9 despite lying 2.4 billion light-years away. Its absolute magnitude of -26.7 makes it roughly 4 trillion times more luminous than the Sun, all from a region smaller than our solar system. The supermassive black hole at its center, estimated at 886 million solar masses, converts infalling matter into radiation with an efficiency of roughly 10%, far exceeding the 0.7% efficiency of hydrogen fusion in stellar cores. This extraordinary efficiency arises from the extreme gravitational potential near the event horizon. Matter falling toward a black hole releases gravitational potential energy as it descends, and in the cramped confines of the inner accretion disk, this energy converts to heat and radiation before the material crosses the point of no return. The exact efficiency depends on the black hole's spin. A non-rotating Schwarzschild black hole allows matter to radiate away roughly 6% of its rest mass energy before crossing the event horizon. A maximally rotating Kerr black hole, spinning at nearly the speed of light, permits efficiencies approaching 42% as the innermost stable circular orbit shrinks closer to the event horizon. Most real black holes fall somewhere between these extremes, with typical efficiencies around 10% explaining the observed luminosities of quasars and other active galactic nuclei. The accretion disk alone cannot account for all the phenomena observed in active galactic nuclei. Many of these objects produce powerful jets, collimated streams of plasma ejected perpendicular to the accretion disk at velocities approaching the speed of light. The jet of M87, visible even in modest telescopes as a luminous spike extending from the galaxy's core, stretches 5,000 light-years into intergalactic space. Radio observations reveal it continues far beyond, inflating enormous lobes of relativistic plasma that span hundreds of thousands of light-years. The energy carried by this jet, estimated at 10 to the 44th ergs per second, rivals the luminosity of the accretion disk itself. The mechanism producing these jets remains an active area of research, but the leading explanation involves the interaction between the black hole's spin, the accretion disk, and magnetic fields. The Blandford-Znajek process extracts rotational energy directly from a spinning black hole through magnetic field lines threading the event horizon. As the black hole rotates, it drags space-time around with it, twisting these magnetic field lines and accelerating charged particles outward along the rotation axis. The result is a tightly focused beam of relativistic plasma, confined by magnetic pressure and capable of maintaining its coherence across intergalactic distances. Blazars represent a special subclass of active galactic nuclei where one of these relativistic jets points almost directly toward Earth. The consequences of this geometric alignment are dramatic. Relativistic beaming, a consequence of special relativity, amplifies the jet's apparent brightness by factors of hundreds or thousands while compressing its variability timescales. A blazar can double its brightness in hours or even minutes, fluctuations that would take months in the rest frame of the jet, but appear compressed by the Doppler effect. Markarian 421, one of the nearest blazars at 400 million light-years, regularly flares in gamma rays, its jet producing photons with energies exceeding 1 trillion electron volts, far beyond what any particle accelerator on Earth can achieve. The spectral energy distribution of a blazar reveals two distinct humps when plotted against frequency. The lower energy hump, peaking in infrared to X-ray wavelengths depending on the source, arises from synchrotron radiation as relativistic electrons spiral around magnetic field lines within the jet. The higher energy hump, extending into gamma rays, results from inverse Compton scattering, where those same relativistic electrons collide with lower energy photons and boost them to extreme energies. The relative heights and positions of these humps encode information about the jet's magnetic field strength, electron population, and bulk velocity, allowing astronomers to probe conditions within these relativistic outflows. The unified model of active galactic nuclei explains the bewildering variety of observed types through orientation effects rather than intrinsic differences. A dusty torus of gas and debris surrounds the central engine, blocking direct views of the accretion disk from certain angles. Observers looking down the jet axis see blazars. Those viewing the disk face-on but outside the jet see quasars, or Seyfert-1 galaxies, with broad emission lines from rapidly moving gas close to the black hole. Observers whose line of sight passes through the dusty torus see only narrow emission lines from more distant gas. classifying the object as a Seyfert 2 galaxy or a radio galaxy. The same physical system appears radically different depending solely on the angle from which we happen to view it. The energy output of active galactic nuclei profoundly influences their host galaxies and beyond. Jets inflate cavities in the hot gas surrounding massive elliptical galaxies, visible as dark bubbles in X-ray images. These cavities, buoyantly rising through the intracluster medium, carry enormous amounts of energy outward. In the Perseus cluster, the central galaxy NGC 1275 has blown bubbles requiring 10 to the 61st ergs to inflate, enough energy to power the Sun for 300 billion years. This mechanical feedback heats the surrounding gas, preventing it from cooling and forming new stars, explaining why massive elliptical galaxies remain red and dead despite sitting in reservoirs of hot gas that should otherwise condense. The quasar era peaked roughly 10 billion years ago, when the universe was only 3 to 4 billion years old. At that epoch, galaxy mergers occurred more frequently, driving gas toward central black holes and triggering widespread nuclear activity. The quasar luminosity function, measuring the number density of quasars at different brightnesses, shows a dramatic decline from that peak to the present day. Modern supermassive black holes, having consumed much of their available fuel and settled into stable configurations, mostly slumber in darkness. Only occasional disturbances, a passing gas cloud, a disrupted star, a minor merger briefly reawaken these ancient engines. The slumbering black holes at galactic centers represent only the most visible manifestation of gravitational influence. Far more pervasive, extending outward to distances 10 times the visible stellar disk, lies a component that emits no light, absorbs no radiation, and reveals itself only through the persistent tug it exerts on everything around it. Dark matter halos envelop galaxies like invisible atmospheres, their mass exceeding the combined total of all stars, gas, and dust by factors of 5 to 10. The Milky Way's stellar disk, spanning roughly 100,000 light-years in diameter, sits embedded within a dark matter halo, extending perhaps 600,000 light-years from the galactic center. This invisible scaffolding contains approximately 1 trillion solar masses of material, dwarfing the 200 to 400 billion solar masses locked in stars. The existence of this unseen component emerged from careful measurements of how galaxies rotate. In the 1970s, astronomer Vera Rubin and her colleagues measured the orbital velocities of stars and gas clouds at increasing distances from galactic centers. If visible matter alone determined gravitational attraction, these velocities should decline with distance, following the same pattern that governs planetary orbits in our solar system. Mercury orbits the Sun at 47 kilometers per second, while Neptune, 30 times more distant, crawls along at merely 5.4 kilometers per second. The gravitational influence of a central mass weakens with the square of distance, and orbital velocities should reflect this decline. Galaxies refused to cooperate with these expectations. Rubin's observations of the Andromeda Galaxy revealed that stars at the outer edges orbited just as quickly as those closer to the center. At 40,000 light-years from Andromeda's core, gas clouds moved at approximately 225 kilometers per second. At 80,000 light-years, they still traveled at 225 kilometers per second. The rotation curve, plotting velocity against distance, remained stubbornly flat rather than declining. This flatness persisted to the outermost measurable regions, far beyond where most visible stars resided. The implications proved inescapable. Either the laws of gravity required modification at galactic scales, or enormous quantities of unseen mass surrounded every galaxy, providing the gravitational pull necessary to maintain these unexpectedly high velocities. Subsequent observations of hundreds of spiral galaxies confirmed the pattern. Nearly all displayed flat rotation curves extending well beyond their visible boundaries. The dark matter required to explain these curves had to be distributed differently than the stars, extending much farther outward and following a density profile that decreased more gradually with distance. Theoretical models developed to describe dark matter halos predict specific density structures. The Navarro-Frenk-White profile, derived from computer simulations of cosmic structure formation, describes halos with density increasing sharply toward the center, proportional to 1 over the radius at small distances, transitioning to 1 over the radius cubed at large distances. This profile successfully reproduces observed rotation curves when combined with the known distribution of visible matter. The concentration parameter, measuring how centrally condensed a halo is, typically ranges from 5 to 15 for galaxy-sized halos, with more massive halos generally showing lower concentrations. The total mass of a dark matter halo can be estimated through several independent methods. Satellite galaxies orbiting larger hosts act as test particles, their velocities revealing the gravitational potential they inhabit. The Milky Way's satellite population, including the large and small Magellanic Clouds, the Sagittarius Dwarf, and dozens of smaller companions, suggests a total halo mass between 1 and 1.5 trillion solar masses. Gravitational lensing provides another probe, as the bending of light from background sources depends on the total mass along the line of sight, regardless of whether that mass emits light. Studies of weak gravitational lensing around stacked images of thousands of galaxies reveal dark matter halos extending to radii of 500 kiloparsecs or more. The formation of these halos preceded the assembly of visible galaxies. In the early universe, dark matter particles, moving slowly enough to be gravitationally bound, began clustering under their own gravity within a few 100 million years after the Big Bang. These primordial dark matter clumps, containing perhaps 1 million solar masses each, merged hierarchically into progressively larger structures. Ordinary matter, still coupled to radiation and unable to collapse on its own, eventually fell into the gravitational wells prepared by dark matter. The halos acted as cosmic cradles, their gravitational potential providing the framework within which gas could accumulate, cool, and eventually form stars. This hierarchical assembly left signatures in halo structure. Simulations revealed that dark matter halos are not smooth, uniform distributions but contain substantial substructure. Smaller halos that merged into larger ones are not completely destroyed. Remnants persist as sub-halos orbiting within the parent structure. The Milky Way's halo likely contains thousands of these sub-halos, ranging from masses comparable to dwarf galaxies down to clumps containing only a few hundred solar masses. Some sub-halos host visible satellite galaxies, but many remain dark, containing no stars at all. The ratio of dark subhalos to luminous satellites may exceed 100 to 1. The shape of dark matter halos deviates from perfect spheres. Simulations consistently produce triaxial structures, elongated along one axis and flattened along another, resembling cosmic footballs more than beach balls. The degree of triaxiality depends on formation history. Halos that experienced recent major mergers tend to be more elongated than those that grew through steady accretion of small clumps. Observational evidence for halo shapes comes from the distribution of satellite galaxies, which preferentially align along the major axis of their host's dark matter distribution, and from the orientation of tidal streams, the stretched remnants of disrupted satellites. The boundary of a dark matter halo remains somewhat arbitrary, as density decreases smoothly with distance rather than dropping abruptly to zero. Astronomers conventionally define halo extent using the virial radius, the distance within which the average density exceeds the cosmic mean by a factor of roughly 200. For the Milky Way, this virial radius lies approximately 300 kiloparsecs from the galactic center, encompassing a volume large enough to contain the Magellanic Clouds and most known satellite galaxies. Beyond this radius, material transitions from being gravitationally bound to the galaxy to participating in the general cosmic expansion. The interaction between dark matter halos and the baryonic matter they contain shapes galactic evolution in subtle ways. Gas falling into a halo shock heats to the virial temperature, determined by the halo's gravitational potential. For Milky Way-sized halos, this temperature reaches several million degrees, hot enough to emit X-rays, but too hot to form stars directly. Cooling processes must extract thermal energy before gas can collapse further. The efficiency of this cooling depends on gas density and metallicity, creating a complex interplay between halo properties and star formation history. Angular momentum transfer between dark matter and baryons influences disk formation. As gas cools and contracts within a halo, it spins up, conserving the angular momentum acquired from cosmological torques during the halo's assembly. The resulting disk size depends on both the total angular momentum and how efficiently that angular momentum is retained during collapse. Interactions between baryons and dark matter substructure can remove angular momentum, producing smaller, more concentrated disks than simple models predict. This angular momentum problem has driven refinements in understanding how galaxies form within their dark matter cradles. The gravitational influence of dark matter extends beyond individual galaxies to shape the cosmic web itself. Halos cluster together, connected by filaments of dark matter that stretch across tens of megaparsecs. Galaxy clusters, the largest gravitationally bound structures in the universe, represent the nodes where multiple filaments intersect. The Virgo cluster, located 54 million light-years away and containing over 1,300 member galaxies, sits within a dark matter halo, massing approximately 10 to the power of 15 solar masses. This single structure outweighs the Milky Way's halo by a factor of nearly 1,000. Detection of dark matter particles remains one of the outstanding challenges in physics. Despite decades of effort, no experiment has definitively identified the particle species responsible for this gravitational scaffolding. Candidates include weakly interacting massive particles, axions, and sterile neutrinos, each with distinct properties and detection signatures. Underground detectors search for the rare interactions between dark matter particles and ordinary atomic nuclei. Space-based instruments look for gamma rays or other radiation produced when dark matter particles annihilate upon encountering each other. The particle nature of dark matter, while gravitationally certain, remains physically mysterious. The gravitational evidence for dark matter emerged not from theoretical speculation, but from careful observation of how galaxies actually rotate. Astronomers measuring the orbital velocities of stars and gas clouds at various distances from galactic centers discovered a profound discrepancy between what Newtonian physics predicted and what the universe revealed. The expectation seemed straightforward. In our solar system, planets closer to the Sun orbit faster than those farther away. Mercury races around its orbit at 47 kilometers per second, while Neptune drifts along at barely 5. This decline in orbital velocity with increasing distance follows directly from Kepler's laws and the concentration of mass at the center. The Sun contains 99.8% of the solar system's mass, so objects at greater distances feel weaker gravitational pull and require less velocity to maintain stable orbits. Galaxies, the reasoning went, should behave similarly. Most of a galaxy's visible light comes from its central bulge and inner disk, where stars crowd together in their greatest concentrations. The outer regions appear progressively dimmer, suggesting less mass. Stars and gas clouds orbiting at the galactic periphery should therefore move more slowly than those closer to the center, their orbital velocities declining in a predictable curve that astronomers call Keplerian fall-off. Vera Rubin and Kent Ford, working at the Carnegie Institution in the 1970s, set out to measure these expected velocity declines in spiral galaxies. Using sensitive spectrographs attached to large telescopes, they recorded the light from hydrogen gas clouds at various distances from galactic centers. The Doppler shift of spectral lines revealed the velocities of these clouds, some approaching Earth and shifting toward blue wavelengths, others receding and shifting toward red. The Andromeda Galaxy, Messier 31, provided one of the first detailed rotation curves. At a distance of 2.5 million light-years, this massive spiral offered an excellent laboratory for studying galactic dynamics. Rubin and Ford measured velocities at distances extending far beyond the bright central regions, out into the dim outer disk where few stars were visible. The results defied expectation. Instead of declining with distance, the orbital velocities remained essentially constant. Gas clouds at 50,000 light-years from Andromeda's center moved at roughly the same speed as those at 20,000 light-years. The rotation curve, rather than falling off, stayed flat. This flatness carries profound implications. For orbital velocity to remain constant at increasing distances, the gravitational pull must also remain constant. But gravitational pull depends on the enclosed mass, the total amount of matter within a given orbital radius. If velocity stays flat while radius increases, then enclosed mass must increase proportionally with distance. Matter must exist in the outer regions of galaxies, matter that produces no detectable light. The mathematics are unambiguous. Orbital velocity equals the square root of gravitational constant times enclosed mass divided by orbital radius. For velocity to remain constant as radius increases, mass must increase linearly with radius. This means galaxies contain vast amounts of matter extending far beyond their visible boundaries, matter distributed in an extended halo rather than concentrated at the center. Subsequent observations confirmed this pattern across hundreds of galaxies. Spiral galaxies of all sizes, from small systems like the Large Magellanic Cloud to giants like the Milky Way, display flat rotation curves. The consistency suggests a universal phenomenon rather than an anomaly specific to particular systems. The Milky Way's own rotation curve has been mapped in exquisite detail. Our Sun orbits the galactic center at approximately 220 kilometers per second, completing one circuit every 230 million years. Stars and gas clouds at twice our distance from the center orbit at nearly the same velocity. The rotation curve remains flat out to at least 60,000 light-years, and indirect evidence suggests it continues flat to even greater distances. Radio astronomers contributed crucial data by observing the 21-centimeter emission line of neutral hydrogen. This radiation penetrates the dust that obscures optical observations, allowing measurements of gas velocities throughout galactic disks and beyond. Hydrogen clouds trace galactic rotation curves to distances where no stars are visible, revealing the gravitational influence of matter that emits no light at any wavelength. The quantity of dark matter implied by flat rotation curves is staggering. In a typical spiral galaxy, the visible stars and gas account for perhaps 10 to 15% of the total mass. The remaining 85 to 90% consists of dark matter distributed in an extended halo. The Milky Way's visible disk contains roughly 100 billion solar masses, but its dark matter halo contains approximately 1 trillion solar masses, 10 times more. Alternative explanations have been proposed and tested. Modified Newtonian dynamics, developed by Mordechai Milgram in 1983, suggests that gravity itself behaves differently at the extremely low accelerations found in galactic outskirts. Rather than invoking unseen matter, this approach modifies the gravitational force law. At accelerations below approximately 1.2 times 10 to the negative 10 meters per second squared, gravity would decline more slowly with distance than Newton's inverse square law predicts. Modified gravity successfully reproduces many observed rotation curves without requiring dark matter. The theory predicts a specific relationship between a galaxy's luminosity and its rotation velocity, a relationship known as the Tully-Fisher relation that observations confirm with remarkable precision. For individual spiral galaxies, the modified gravity approach often matches observations as well as dark matter models. However, galaxy clusters present a challenge. The gravitational lensing and velocity dispersions observed in clusters require more mass than modified gravity alone can provide. Even with altered gravitational physics, clusters appear to contain substantial amounts of unseen matter. The bullet cluster, where the gravitational center determined by lensing is offset from the visible gas, provides particularly compelling evidence that dark matter exists as a distinct substance rather than a modification of gravity. Dwarf galaxies offer another testing ground. These small systems, containing only millions to billions of stars, show enormous variation in their dark matter content. Some dwarf spheroidal galaxies orbiting the Milky Way have mass-to-light ratios exceeding 1,000, meaning their total mass is 1,000 times what their stars alone would suggest. The Draco dwarf spheroidal, located approximately 260,000 light-years from Earth, contains only a few 100,000 stars, but moves under the gravitational influence of tens of millions of solar masses of dark matter. Other dwarf galaxies appear nearly devoid of dark matter. NGC 1052, discovered in 2018, rotates at velocities consistent with its visible stellar mass alone. This galaxy, located approximately 65 million light-years away, may have lost its dark matter through tidal interactions with a larger neighbor. The existence of such dark matter-deficient galaxies actually supports the dark matter hypothesis, demonstrating that luminous matter and dark matter can be separated under the right conditions. The distribution of dark matter within halos follows characteristic patterns. Numerical simulations predict that dark matter density increases toward galactic centers, following a profile first described by Julio Navarro, Carlos Frenk, and Simon White in 1996. This NFW profile has density proportional to 1 over radius times the quantity 1 plus radius over scale radius squared. The central regions show a cuspy density enhancement, while the outer regions decline more gradually. Observations sometimes conflict with these predictions. Many dwarf galaxies appear to have constant density cores rather than the cuspy centers simulations predict. This core cusp problem remains an active area of research. Possible solutions include the effects of stellar feedback, where supernovae and stellar winds redistribute both ordinary and dark matter, or modifications to the properties of dark matter particles themselves. The total dark matter content of the universe has been measured through multiple independent methods. Cosmic microwave background observations indicate that dark matter comprises approximately 27% of the universe's total energy density, while ordinary matter accounts for only 5%. The remaining 68% consists of dark energy, the mysterious component driving cosmic acceleration. Within galaxies, dark matter and ordinary matter interact only through gravity. This gravitational coupling shapes the formation and evolution of galactic structure. Dark matter halos provide the gravitational welds into which ordinary matter falls, the scaffolding upon which visible galaxies are built. Without dark matter, the universe would contain far fewer galaxies, and those that formed would be smaller and less structured than what we observe. The rotation curves that first revealed dark matter continue to provide insights into galactic structure. Modern surveys measure velocities for millions of stars using space-based observatories like Gaia, building three-dimensional maps of galactic dynamics with unprecedented precision. These observations confirm the presence of dark matter while revealing its detailed distribution, the invisible architecture that shapes the islands of light we call galaxies. The visible stars that trace galactic rotation curves represent only a fraction of the ordinary matter within galaxies. Between the stars lies the interstellar medium, a tenuous but crucial reservoir of gas and dust that spans the space between stellar systems. This material, though diffuse beyond anything achievable in terrestrial laboratories, contains the raw ingredients for future generations of stars and preserves the chemical legacy of all the stars that came before. The interstellar medium within a typical spiral galaxy like the Milky Way contains roughly 10 to 15% of the total baryonic mass, amounting to perhaps 10 to 50 billion solar masses of gas spread across a disk spanning 100,000 light-years. This material exists at extraordinarily low densities, averaging perhaps 1 atom per cubic centimeter in the general interstellar space. For comparison, the best laboratory vacuums on Earth contain roughly 10 billion molecules per cubic centimeter, making the interstellar medium a vacuum far more perfect than anything human technology can produce. Yet this near emptiness proves far from uniform. The interstellar medium organizes itself into distinct phases, each characterized by different temperatures, densities, and physical states. The hot ionized medium, heated to temperatures exceeding 1 million Kelvin, fills perhaps half the volume of the galactic disk. This tenuous plasma, with densities as low as 1 particle per 10,000 cubic centimeters, represents gas heated by supernova explosions and stellar winds. Despite its high temperature, this phase contains relatively little mass because of its extreme diffuseness. The warm ionized medium occupies a smaller volume, but contributes significantly to the total gas mass. At temperatures around 8,000 Kelvin and densities of roughly 1/10 of a particle per cubic centimeter, this phase traces regions ionized by ultraviolet radiation from hot stars. The warm neutral medium, at similar temperatures but composed of neutral hydrogen atoms, fills much of the remaining volume. These warm phases together account for the bulk of the interstellar space between denser structures. The cold neutral medium represents a dramatic transition. At temperatures between 50 and 100 Kelvin, neutral hydrogen atoms cluster into clouds with densities of 20 to 50 particles per cubic centimeter. These cold clouds, though occupying only a few percent of the galactic volume, contain a substantial fraction of the total gas mass. The clouds drift through the warmer surrounding medium, like fog banks moving through clear air, their boundaries maintained by pressure equilibrium between the different phases. Molecular clouds represent the densest phase of the interstellar medium. Within these structures, temperatures drop to 10 or 20 Kelvin, cold enough for hydrogen atoms to combine into molecular hydrogen. Densities climb to hundreds or thousands of particles per cubic centimeter, with the densest cores reaching millions of particles per cubic centimeter. These molecular clouds, containing masses ranging from a few hundred to several million solar masses, serve as the exclusive sites of star formation in the modern universe. The transition from atomic to molecular gas requires shielding from ultraviolet radiation that would otherwise dissociate hydrogen molecules. Dust grains, tiny particles of silicates, and carbonaceous material measuring fractions of a micrometer across provide this shielding, while also serving as the surfaces upon which hydrogen molecules form. The dust-to-gas ratio in the Milky Way amounts to roughly 1% by mass, a small fraction that nonetheless plays an outsized role in interstellar chemistry and thermal regulation. The chemical composition of the interstellar medium records the cumulative history of stellar nucleosynthesis. Primordial gas from the Big Bang contained only hydrogen, helium, and trace amounts of lithium. Every heavier element, what astronomers collectively call metals, despite the chemical imprecision of the term, was forged within stellar interiors or during stellar explosions. The metallicity of interstellar gas, typically measured as the ratio of iron to hydrogen compared to solar values, varies systematically across galactic structures. In the Milky Way, metallicity decreases with distance from the galactic center. The inner disk, where star formation has proceeded most vigorously over cosmic time, shows metallicities roughly twice the solar value. The outer disk, with its lower star formation rates and longer gas consumption timescales, contains gas at perhaps half solar metallicity. This gradient reflects the inside-out growth of the galactic disk, with the central regions forming stars earlier and more efficiently than the periphery. The vertical structure of the disk shows similar patterns. Gas and young stars concentrate within a thin layer, perhaps 300 light-years thick, while older stellar populations extend into a thicker disk spanning several thousand light-years. The metallicity of stars correlates with their vertical distribution, with metal-poor stars showing larger scale heights. This correlation reflects the gradual enrichment of the interstellar medium over time, with older stars forming from less processed material. Stellar feedback drives the cycling of material between phases of the interstellar medium. Massive stars, those exceeding 8 solar masses, live fast and die violently. During their brief main sequence lifetimes of only a few million years, they emit copious ultraviolet radiation that ionizes surrounding gas and creates expanding bubbles of hot plasma. Their powerful stellar winds, flowing outward at speeds of 1,000 to 3,000 kilometers per second, sweep up interstellar material into dense shells. When these massive stars exhaust their nuclear fuel, they explode as core collapse supernovae, releasing roughly 10 to the 51 ergs of kinetic energy into the surrounding medium. This energy, equivalent to the total luminous output of the Sun over its entire 10 billion-year lifetime, drives expanding shock waves that heat gas to millions of Kelvin and accelerate it to velocities of thousands of kilometers per second. A single supernova can sweep up and heat several thousand solar masses of interstellar material, creating a hot bubble that persists for hundreds of thousands of years before cooling and merging with the ambient medium. The collective effect of multiple supernovae in regions of active star formation creates superbubbles, vast cavities of hot gas extending hundreds of light-years across. When these bubbles break through the thin gas layer of the galactic disk, they vent hot material into the galactic halo in structures called chimneys. This hot gas rises above the disk, cools radiatively over millions of years, and eventually falls back as a galactic fountain, recycling material between the disk and halo. Type Y are supernovae, arising from white dwarf stars in binary systems, contribute additional energy and heavy elements to the interstellar medium. These explosions occur in older stellar populations, with a delay of roughly 1 billion years after star formation. Each Type Ia supernova synthesizes approximately 6/10 of a solar mass of iron, making these events the primary source of iron group elements in the universe. The rate of Type Ia supernovae in a galaxy like the Milky Way amounts to roughly 1 every few hundred years, a steady drip of iron enrichment continuing long after the most massive stars have died. The chemical yields from different types of stellar deaths imprint characteristic abundance patterns on the interstellar medium. Core collapse supernovae, arising from massive stars, produce primarily oxygen, neon, magnesium, and silicon, the so-called alpha elements. Type Ia supernovae produce iron peak elements. The ratio of alpha elements to iron in stellar atmospheres therefore records the relative contributions of these two enrichment channels, providing a chemical clock for stellar populations. Stars in the galactic halo, formed early in the Milky Way's history, show enhanced alpha to iron ratios. This pattern indicates formation from gas enriched primarily by core collapse supernovae, before type Ia supernovae had time to contribute their iron. Thin disk stars, formed more recently from well-mixed interstellar gas, show solar abundance ratios reflecting the accumulated contributions of both supernova types over billions of years. Asymptotic giant branch stars, the final evolutionary phase of intermediate mass stars between 1 and 8 solar masses, contribute additional elements to the interstellar medium. These stars shed their outer layers through slow stellar winds, enriching the surrounding gas with carbon, nitrogen, and heavy elements produced through the slow neutron capture process. The carbon stars visible in nearby galaxies represent this evolutionary phase, their distinctive red colors arising from carbon-rich atmospheres. The most massive stars, those exceeding roughly 25 solar masses, may end their lives as hypernovae or gamma-ray bursts, explosions even more energetic than typical supernovae. These events synthesize heavy elements through the rapid neutron capture process, producing gold, platinum, uranium, and other elements heavier than iron. Neutron star mergers, the collision of two stellar remnants in decaying binary orbits, provide another site for rapid neutron capture nucleosynthesis. The detection of gravitational waves from neutron star merger GW170817 in 2017, accompanied by electromagnetic observations showing the signatures of heavy element production, confirmed this enrichment channel. The cycling of material through stars and back into the interstellar medium operates on timescales ranging from millions to billions of years. Massive stars complete their life cycles in a few million years, rapidly returning processed material to the interstellar medium. Solar mass stars live for 10 billion years, locking up their material for cosmologically significant periods before returning it through planetary nebula ejection. The integrated effect of these different timescales produces the gradual enrichment observed in stellar populations of different ages. Gas consumption through star formation depletes the interstellar medium over time. The current star formation rate in the Milky Way, roughly 1 to 3 solar masses per year, would exhaust the available gas supply in a few billion years without replenishment. Gas infall from the circumgalactic medium, the diffuse halo of gas extending beyond the visible disk, provides fresh material that sustains ongoing star formation. High-velocity clouds, concentrations of neutral hydrogen falling toward the galactic disk at speeds of 100 to 400 kilometers per second, represent this accretion in action. The balance between gas consumption, stellar feedback, and fresh accretion determines the long-term evolution of galactic star formation. This balance varies across cosmic time and between different galactic environments, shaping the diverse population of galaxies observed in the universe today. The delicate balance between gas consumption and replenishment faces its most dramatic disruption when galaxies encounter one another across the cosmic web. These gravitational interactions, ranging from gentle tidal disturbances to catastrophic mergers, represent the most transformative events in galactic evolution, reshaping stellar distributions, triggering explosive bursts of star formation, and fundamentally altering the physical nature of the systems involved. Galaxies do not exist in isolation. The same large-scale structure that channels gas in fall also guides galaxies along filamentary paths that inevitably bring them into proximity with their neighbors. Within galaxy clusters, number densities reach hundreds of galaxies per cubic megaparsec, making interactions frequent and consequential. Even in less crowded environments, gravitational attraction draws neighboring systems together over billions of years, their relative velocities and orbital parameters determining whether they experience brief tidal encounters or complete coalescence. The physics of galactic interaction begins with the differential gravitational force across an extended body. When two galaxies approach within several hundred kiloparsecs, the near side of each system experiences stronger gravitational attraction toward the companion than the far side. This tidal force, proportional to the mass of the perturbing galaxy and inversely proportional to the cube of the separation distance, stretches each system along the line, connecting their centers while compressing it perpendicular to this axis. The mice galaxies, NGC 4676a and NGC 4676b, located approximately 290 million light-years away in the constellation Coma Berenices, display the characteristic signatures of this tidal stretching. Long tails of stars and gas extend outward from each galaxy, drawn out by gravitational forces during their close passage roughly 160 million years ago. These tidal tails contain material stripped from the outer regions of each disk, where the gravitational binding to the parent galaxy proved insufficient to resist the perturbing force. The tails extend over 300,000 light-years, longer than the combined diameters of the original galaxies, carrying with them roughly 10% of the total stellar mass. The formation of tidal tails follows predictable physical principles rooted in orbital mechanics and energy transfer. Material on the side of a galaxy facing its companion experiences a net acceleration toward the perturber, while material on the opposite side feels a relative acceleration away from it. During a prograde encounter, where the orbital motion of the companion aligns with the rotation of the disk, resonant coupling amplifies these perturbations. Stars and gas at certain radii find their orbital periods matching the timescale of the gravitational disturbance, allowing energy to accumulate over multiple orbital passages. The antennae galaxies, NGC 4038 and NGC 4039, provide perhaps the most studied example of an ongoing major merger. Located 45 million light-years away in the constellation Corvus, these two spiral galaxies began their interaction approximately 600 million years ago and have since completed multiple close passages. Their tidal tails extend over 500,000 light-years, while their central regions have begun to coalesce into a single chaotic structure. Infrared observations reveal that the interaction has triggered star formation rates exceeding 20 solar masses per year, roughly 10 times the combined rate of the progenitor galaxies before their encounter. This enhancement of star formation during mergers results from the compression and concentration of interstellar gas. While stars pass through one another like two swarms of bees, their average separations too vast for direct collisions, the gas components of merging galaxies cannot avoid interaction. Colliding gas clouds shock, compress, and lose angular momentum through dissipative processes. This angular momentum loss causes gas to flow inward toward the centers of the merging systems, accumulating in dense concentrations that become sites of vigorous star formation. Numerical simulations of galaxy mergers, tracking the gravitational interactions of millions of particles representing stars, gas, and dark matter, reveal the detailed physics of these encounters. The outcome depends sensitively on the mass ratio of the interacting galaxies, their relative velocities, the geometry of their approach, and the gas fractions of each system. Major mergers involving galaxies of comparable mass within a factor of 3 produce the most dramatic transformations. Minor mergers, where the mass ratio exceeds 4:1, cause less severe disruption to the larger system while completely destroying the smaller companion. The merger timescale, from first approach to final coalescence, spans hundreds of millions to several billion years, depending on the orbital parameters. Galaxies on nearly radial orbits plunge through one another quickly, while those on more circular trajectories spiral inward gradually as dynamical friction transfers orbital energy to the stellar and dark matter components. This friction arises because the gravitational wake trailing behind each galaxy as it moves through the other creates a net retarding force, slowing the relative motion and causing the orbits to decay. During the final stages of coalescence, the ordered rotation of spiral disks transforms into the random stellar motions characteristic of elliptical galaxies. This process, called violent relaxation, occurs as the rapidly changing gravitational potential redistributes stellar energies over timescales comparable to the dynamical time of the system. Stars that previously followed nearly circular orbits in a disk find themselves on elongated, randomly oriented trajectories through a more spheroidal mass distribution. The Milky Way itself bears evidence of past merger activity. The Gaia spacecraft, measuring the positions and velocities of over 1 billion stars with unprecedented precision, has revealed streams and structures in the stellar halo that trace the remnants of accreted satellite galaxies. The Gaia Enceladus structure, also called the Gaia sausage for its distinctive elongated distribution in velocity space, represents the debris of a galaxy roughly 1/4 the mass of the young Milky Way that merged with our galaxy approximately 10 billion years ago. This ancient collision deposited roughly 500 million solar masses of stars into the inner halo and may have heated the early Milky Way disk, contributing to the thick disk component observed today. The supermassive black holes at the centers of merging galaxies follow their own evolutionary path during these interactions. Initially separated by the full distance between the galactic nuclei, the black holes sink toward the center of the merged system, through dynamical friction against the surrounding stars. This process efficiently reduces their separation from kiloparsecs to parsecs over timescales of hundreds of millions of years. Below separations of roughly 1 parsec, dynamical friction becomes inefficient as fewer stars occupy orbits that can interact with the black hole binary. The subsequent evolution of supermassive black hole binaries remains an active area of research, sometimes called the final parsec problem. Three-body interactions with individual stars, gravitational torques from surrounding gas, and eventually gravitational wave emission must combine to drive the binary toward coalescence. When the black holes finally merge, they release gravitational waves detectable by pulsar timing arrays for the most massive systems, with total energies equivalent to several percent of the combined black hole mass converted to gravitational radiation. The starburst activity triggered by major mergers produces some of the most luminous galaxies in the universe. Ultraluminous infrared galaxies, or ULIRGs, emit more than 1 trillion solar luminosities, primarily at infrared wavelengths, where dust heated by young stars re-radiates absorbed optical and ultraviolet light. ARP 220, located 250 million light-years away, represents the prototypical ULIRG, formed from the merger of 2 gas-rich spiral galaxies. Its central region, spanning only a few hundred parsecs, contains molecular gas densities exceeding 10,000 hydrogen molecules per cubic centimeter, and star formation rates approaching 200 solar masses per year. The intense star formation in merger-driven starbursts cannot sustain itself indefinitely. The rapid consumption of available gas, combined with the feedback from massive stars and supernovae, eventually exhausts the fuel supply and quenches further star formation. Simulations suggest that major mergers of gas-rich spirals produce elliptical galaxies with old red stellar populations within 1 to 2 billion years after the final coalescence, transforming blue, star-forming systems into red, quiescent ones. Not all galactic interactions lead to merger. High-velocity encounters, particularly common in massive galaxy clusters where velocity dispersions exceed 1,000 kilometers per second, allow galaxies to pass through one another without becoming gravitationally bound. These flyby interactions still produce tidal disturbances, stripping material from outer regions and triggering modest enhancements in star formation. But the galaxies ultimately separate and continue on independent trajectories. The Andromeda Galaxy, Messier 31, approaches the Milky Way at approximately 110 kilometers per second, closing the current separation of 2.5 million light-years. In roughly 4.5 billion years, the two galaxies will experience their first close passage, with tidal forces beginning to distort their disks. Complete merger will follow over the subsequent 2 billion years, producing a single elliptical galaxy, sometimes called Milkdromeda. The Sun, if it still exists at that time, will likely survive the merger, relocated to a new orbit within the combined system, though the night sky will transform beyond recognition as the familiar spiral structure dissolves into a smooth ellipsoidal glow. The transformation of spiral structure into ellipsoidal smoothness represents just one pathway toward galactic quiescence. Across the universe, galaxies cease forming stars through multiple mechanisms, each leaving distinct signatures in their stellar populations and gas content. Understanding these processes reveals why the universe's star formation rate has declined by a factor of 10 since its peak roughly 10 billion years ago, and why so many galaxies today drift through space as passive collections of aging stars. The most fundamental requirement for star formation is cold, dense gas capable of gravitational collapse. Without fresh supplies of hydrogen and helium flowing inward from the cosmic web, galaxies gradually exhaust their existing reservoirs. This process, termed starvation or strangulation, operates on timescales of several billion years as existing gas converts into stars without replenishment. A typical spiral galaxy like the Milky Way contains approximately 5 billion solar masses of molecular hydrogen, enough to sustain star formation at current rates for perhaps 2 billion years. But the Milky Way also accretes roughly 1 solar mass of fresh gas per year from its surrounding circumgalactic medium, roughly balancing the consumption rate. Interrupt this inflow, and the galaxy's star-forming future becomes finite. The circumgalactic medium itself extends outward to approximately 300 kiloparsecs, a diffuse halo of gas at temperatures ranging from 10,000 to several million Kelvin. This reservoir contains mass comparable to or exceeding the stellar mass of the galaxy it surrounds, representing the raw material for future star formation. Observations using quasar absorption lines reveal that this gas carries metallicity levels between 1% and 30% of solar values, indicating a mixture of primordial material and gas previously processed through stellar nucleosynthesis and expelled by galactic winds. The fate of this circumgalactic reservoir determines whether a galaxy continues forming stars or gradually fades into quiescence. Environmental factors dramatically accelerate the transition from active to passive states. Galaxies falling into massive clusters encounter the intracluster medium, a hot plasma filling the space between cluster members with temperatures reaching 100 million Kelvin and densities of approximately 1 particle per 1,000 cubic centimeters. Though extraordinarily tenuous by terrestrial standards, this medium exerts significant pressure on galaxies moving through it at velocities of 1,000 to 2,000 kilometers per second. Ram pressure stripping occurs when this dynamic pressure exceeds the gravitational restoring force binding gas to a galaxy's disk. The pressure scales with the intracluster medium density multiplied by the square of the galaxy's velocity through it. For a galaxy moving at 1,500 kilometers per second through a medium with density of 3 times 10 to the negative 27 grams per cubic centimeter, the ram pressure reaches approximately 10 to the negative 11 pascals. This seemingly minuscule pressure, sustained over millions of years, proves sufficient to remove loosely bound gas from galactic outskirts while leaving the more tightly bound central regions temporarily intact. The Virgo cluster, located approximately 54 million light-years from Earth, provides numerous examples of ram pressure stripping in action. NGC 4522, a spiral galaxy falling into Virgo at roughly 1,300 kilometers per second, displays a truncated gas disk extending only about half the radius of its stellar disk. Hydrogen gas trails behind the galaxy in a wake extending tens of thousands of light-years, visible in radio observations as emission at the 21 centimeter wavelength characteristic of neutral hydrogen. The stripped gas eventually disperses into the intracluster medium, lost to the galaxy forever. Even more dramatic examples exist closer to Virgo's center, where the intracluster medium reaches its highest density. NGC 4438, located just 400,000 light-years from the massive elliptical M87, has lost nearly all its interstellar gas to a combination of ram pressure and tidal interactions with neighboring galaxies. Its stellar disk remains intact, but the galaxy has effectively ceased forming new stars, transitioning from a gas-rich spiral to what astronomers term an anemic spiral, retaining spiral structure in its stars, but lacking the gas necessary to maintain that structure over cosmic time. The timescale for complete gas removal depends on both the galaxy's mass and its trajectory through the cluster. A Milky Way mass galaxy on a radial orbit passing through the cluster core might lose its outer gas disk within 500 million years, while a galaxy on a more circular orbit at larger cluster-centric distances might retain significant gas for several billion years. Dwarf galaxies, with their shallower gravitational potential wells, prove far more vulnerable. The Fornax cluster, at a distance of 62 million light-years, contains numerous dwarf elliptical galaxies that likely entered the cluster as gas-rich dwarf irregulars before ram pressure stripped their star-forming material. Beyond ram pressure, gravitational interactions within dense environments contribute to gas removal through tidal stripping. Repeated high-speed encounters between cluster galaxies, termed harassment, gradually heat stellar orbits and remove loosely bound material from galactic outskirts. Unlike the dramatic tidal tails produced by slow galaxy mergers, harassment produces more subtle effects, thickening galactic disks and truncating their outer regions without triggering major starbursts. The cumulative effect of dozens of such encounters over several billion years transforms late-type spiral galaxies into earlier morphological types, contributing to the observed correlation between galaxy morphology and local density. The hot gas halos surrounding massive galaxies face their own removal mechanism within clusters. Thermal evaporation occurs when the cooler circumgalactic gas contacts the much hotter intra-cluster medium, with heat conduction gradually raising the halo gas temperature until it becomes indistinguishable from its surroundings. This process removes the reservoir that would otherwise cool and replenish the galaxy's star-forming disk, ensuring long-term quiescence even if the disk gas survives initial ram pressure stripping. Internal processes also drive galaxies toward quiescence without requiring environmental triggers. The supermassive black holes discussed in earlier passages can regulate or terminate star formation through energetic feedback. When actively accreting, these black holes launch jets and winds that heat surrounding gas, preventing the cooling flows that would otherwise deliver fresh material to the galactic disk. This feedback mechanism explains why the most massive galaxies hosting the most massive black holes tend to be the most thoroughly quenched, their star formation rates suppressed by factors of 100 or more compared to their gas content alone would predict. The energy budget for this suppression proves remarkable. A supermassive black hole, accreting at just 1% of its Eddington limit, releases energy equivalent to the gravitational binding energy of its host galaxy's gas supply over timescales of hundreds of millions of years. Even inefficient coupling between this energy output and the surrounding gas suffices to maintain temperatures above the threshold for gravitational collapse. Observations of massive elliptical galaxies reveal hot X-ray emitting gas halos at temperatures of 10 to 50 million Kelvin, maintained against radiative cooling by intermittent black hole activity. The transition from star-forming to quiescent states leaves permanent signatures in galactic stellar populations. Actively star-forming galaxies appear blue due to the presence of short-lived luminous O and B-type stars with surface temperatures exceeding 20,000 Kelvin. Once star formation ceases, these massive stars exhaust their fuel within tens of millions of years, leaving behind progressively cooler and redder stellar populations. A galaxy that ceased forming stars 5 billion years ago now appears dominated by G and K-type stars similar to the Sun, with colors shifted toward the red end of the spectrum. Spectroscopic observations reveal even more detailed histories. The presence or absence of specific absorption features, particularly the hydrogen-Balmer lines and the 4,000 angstrom break produced by ionized calcium, allows astronomers to estimate when star formation ceased and how abruptly the transition occurred. Galaxies that experienced rapid quenching, with star formation timescales dropping from billions of years to essentially zero within a few 100 million years, display different spectral signatures than those that faded gradually through starvation. The cosmic census of quiescent galaxies reveals their increasing dominance over time. At redshift 2, corresponding to roughly 10 billion years ago, approximately 80% of galaxies with stellar masses exceeding 10 billion solar masses were actively forming stars. Today, that fraction has reversed, with roughly 80% of similarly massive galaxies classified as quiescent. The universe's star formation rate density peaked between redshifts 1 and 3 and has declined steadily since, as gas reservoirs deplete and environmental quenching mechanisms accumulate their effects. Looking forward across cosmic time, the fate of all galaxies trends toward eventual quiescence. The cosmic web continues delivering gas to galaxies, but the rate of this delivery declines as the universe expands and the average density of intergalactic gas decreases. Even isolated galaxies, protected from environmental stripping, will eventually exhaust their gas supplies and fade. The Milky Way itself, despite its current healthy star formation rate of approximately 1 to 2 solar masses per year, will likely cease forming stars within 5 to 7 billion years as its gas reservoir depletes and the merger with Andromeda disrupts its spiral structure. The final stellar populations of quenched galaxies age gracefully but inexorably. Red giant stars shed their outer layers as planetary nebulae, enriching the interstellar medium with processed elements, but contributing negligible mass to future star formation. White dwarfs cool over billions of years, fading from luminosities of 1% solar to 1/1,000,000th solar and below. The galaxies themselves persist as gravitationally bound collections of stellar remnants, their light output declining by factors of thousands as the last red dwarfs exhaust their hydrogen fuel over timescales of trillions of years. leaving behind only the faint infrared glow of cooling stellar corpses drifting through an ever-expanding, ever-darkening cosmos.